This next chapter is all about radicals. To set this up, let's take some notes about what radicals are and then start talking about how we can simplify radicals. First, with radicals, you're going to have this root symbol with something underneath it and then a number written up inside the little loop of the root. We call that number on the inside the index. And what we're working with most of the time is going to be a square root. So for example, if I've got the square root of something like a to the 7th. Notice on this one there's no index. When there's no index written, we're going to assume that means square root or an index of 2. It's invisible. We don't write the index of 2. And the idea is it wants to simplify perfect squares out of the radical. Which means if I think about a to the 7th as a squared times a squared times a squared times a, notice that's 7 a's underneath the radical. I can take a square root of a squared to get a square root of a squared to get a, and a square root of a squared to get a, and that leaves behind a single a inside the radical. Well, a times a times a is a cubed, and so we end up with a cubed times the square root of a. And what I want to notice here is if I had taken my exponent and divided it by the index, 7 divided by 2 is 3 remainder 1. Notice 3 a's came out and 1 a remained inside. That could have been a shortcut we could have done. And in fact, that is the shortcut that we will do in order to simplify this, is we'll take the exponent and divide it by the index to see how many things can come out of that radical. And any leftovers, any remainders, will remain inside the radical. And in fact, this works not just for letters, but it also works for numbers. If we first find the prime factorization of the number. So let's take a look at some examples of what that might look like and what that might mean. Let's first start with the square root of 48. If I wanted to simplify the square root of 48, because that's a number, we're going to find the prime factorization of 48. It's divisible by 2 24 times. Circle the prime. It's divisible by 2 12 times. Circle the prime. It's divisible by 2 6 times. Circle the prime. It's divisible by 2 3 times. Putting that all together then underneath the square root, 48 is 2 to the 4th power, because there's 4 of them, times 3. Then to decide how many 2's are allowed outside of the square root, we'll divide the exponent by the index. And remember, if no index is written, it's 2. 4 divided by 2 is 2. So I'm going to pull out 2 of that base, or 2 squared, outside the radical, leaving behind a 3. And 2 squared is 4. So maybe a better way to write that would be 4 root 3 is the simplified form of the square root of 48. This also works with letters. Let's try doing the square root of a to the 5th, b to the 8th, c to the 15th. Again, the index is not written, so we assume it's a 2. And to decide how many a's come outside of the radical, I'll take the 5 divided by 2. Well, 5 divided by 2 is 2 with a remainder of 1. So 2 a's come out, a squared, and 1 remains inside. Same thing with the b's. It's b to the 8th. 8 divided by 2 is 4. So b to the 4th comes out of the radical. Same thing for the c's. C to the 15th. 15 divided by 2 is 7, remainder 1. So 7 come out, and 1 remains behind. And so we end up with a squared b to the 4th, c to the 7th, times the square root of ac. Let's try one that combines numbers and letters in it. Let's try 9 times the square root of 250 x to the 4th y z to the 5th. Well, to see what can come out of the root, we first need to factor that 250. 250 is divisible by 2, circle the prime, 125 times, which is divisible by 5, 25 times, which is divisible by 5, 5 times. So really, we have 9 times the square root of a 2, a 5 cubed, x to the 4th, a y, and a z. And then let's decide what comes out and what remains in the radical. There's already a 9 outside of the radical. The 2 has no exponent on it, so it has to stay. With the 5 cubed, though, I can divide the exponent by 2. 3 divided by 2 is 1, so 1 5 comes out, and 1 5 remains behind, because 3 divided by 2 is 1 remainder 1. X to the 4th, 4 divided by 2 is 2, so x squared comes out. Oops, and I forgot to copy the exponent on the z of 5. But y has no exponent, can't do anything with it. But z's exponent of 5, 5 divided by 2 is going to be 2, remainder 1, and so 1 remains behind. Finish simplifying by multiplying. 9 times 5 is 45. X squared z squared times the square root of 2 times 5 is 10, yz. And now we have simplified that radical by dividing the exponents by the index to see what's allowed to break free from the radical. In our next video, we're going to look at how this can help us add and subtract radicals together.